Far beyond the bright orbit of Jupiter, beyond the familiar line of Saturn's rings, there is a moon hidden beneath an orange atmosphere. Its name is Titan. From space, its surface cannot be seen in ordinary light. The atmosphere is too thick, filled with nitrogen and suspended organic particles that scatter sunlight into a muted amber haze. Mountains, dunes, river channels, impact craters, and dark northern seas remain concealed below, as though the entire world has drawn a curtain across itself. In July of 2028, a spacecraft is scheduled to begin the long journey toward that hidden landscape. It will not arrive as a rover. It will not remain fixed beside a single landing site. It will carry 8 rotors, arranged in 4 pairs, and after descending through Titan's atmosphere, it will rise from the ground and fly. The mission is called Dragonfly. Its design resembles a large drone, but its purpose reaches far beyond flight. Dragonfly will be a mobile laboratory, built to cross Titan's surface from one scientifically valuable location to another. It will land, examine the ground, collect samples, measure the atmosphere, listen for movements within the moon, and then lift away again. Titan makes this possible. Its gravity is only a fraction of Earth's, while its atmosphere near the surface is denser than our own. A machine that would struggle to carry itself through Earth's air can fly more efficiently there, supported by thick nitrogen beneath its blades. The same conditions that hide Titan's surface from distant telescopes may allow Dragonfly to explore that surface in a way no wheeled vehicle could. The journey to Titan will take roughly 6 years. By the time Dragonfly approaches Saturn's largest moon in late 2034, it will have crossed well over 1 billion kilometers of interplanetary space. Then the spacecraft will separate from its cruise stage and enter an atmosphere no human-built rotorcraft has ever entered before. There will be no pilot guiding it in real time. Signals between Earth and Titan take more than an hour to travel each way, depending on the distance between the planets. Dragonfly must therefore understand its surroundings, select safe ground, and carry out much of its movement independently. Its cameras, sensors, navigation systems, and onboard computers will work together while mission teams on Earth receive information from events that have already happened. The first landing is planned for a region of broad equatorial dunes. These dark fields stretch across Titan for immense distances. They are not made from familiar desert sand, but from carbon-rich material shaped by winds beneath the haze. Between the dunes are flatter areas where Dragonfly may find safer ground, places where its instruments can begin reading the chemistry of another world. From there, the mission will slowly widen. Over more than 3 Earth years, Dragonfly may visit dozens of locations and travel about 115 kilometers. Each flight will carry it across terrain that remained almost completely unknown until the Cassini spacecraft began mapping Titan from orbit and the Huygens probe briefly reached the surface in 2005. Dragonfly will continue that exploration, but it will not stay where it lands. It will move from dunes toward older terrain, and eventually toward the region around Selk crater, where an impact may once have brought liquid water into contact with the complex organic material covering Titan's surface. That meeting of water and carbon lies near the center of the mission. Dragonfly is not traveling to Titan because scientists expect to find animals, plants, or cities beneath the haze. It is going there to study something earlier and quieter, the chemistry that can exist before life, the molecular pathways that may begin when energy, organic matter, and liquid environments come together. The journey begins on Earth inside clean rooms and test chambers where the first parts of the flying are taking shape, but its destination waits under an orange sky. Long before Dragonfly had a name, Titan was only a point of light moving beside Saturn. The Dutch astronomer Christian Huygens first recognized it as a moon in 1655. Through the small telescopes of that era, there was no orange atmosphere, no landscape, and no hint of rivers or seas. There was only a distant companion circling a planet whose rings were still difficult to understand. For centuries, Titan remained unresolved. Astronomers could measure its orbit and estimate its size, but the moon itself offered little detail. Its surface was hidden, and even large telescopes could not see through the veil surrounding it. By the early 20th century, observations had begun to suggest that Titan possessed an atmosphere. Later measurements showed that this atmosphere was not thin or temporary. It was deep, dense, and dominated by nitrogen. That alone made Titan unusual. Most moons in the solar system are exposed directly to space. Their surfaces meet vacuum, and the marks left by impacts can remain almost unchanged for immense spans of time. Titan is different. Its ground lies beneath weather. Winds cross its plains, clouds form and dissolve, rain falls. Rivers carry liquid through branching channels, lakes and seas gather in low regions near the poles. The liquid is not water. At Titan's surface temperature, water behaves like rock. It forms the hard crust beneath the landscape, while methane and ethane can move between vapor, cloud, rain, and liquid reservoirs. The familiar pattern of Earth's water cycle appears there in another chemical form. Sunlight warms Titan only faintly. Saturn and its moons orbit roughly 10 times farther from the Sun than Earth does. From Titan's surface, the Sun would appear much smaller, and much of its light would be filtered through the atmospheric haze before reaching the ground. The average surface temperature is close to -290 degrees Fahrenheit. Yet the air is thick. Pressure at the surface is about 50% greater than the pressure at sea level on Earth. A person somehow standing there would not be surrounded by the emptiness found on the Moon or Mars. There would be a substantial atmosphere pressing from every direction, carrying winds, suspended particles, and the products of chemical reactions taking place high above. Those reactions begin with sunlight and energetic particles striking nitrogen and methane in Titan's upper atmosphere. The molecules are broken apart, their fragments meet, rearrange, and form more complicated compounds. Some gather into small particles that descend through the atmosphere, creating the haze that gives Titan its orange color. Over time, this carbon-rich material settles onto the dunes, plains, craters, and frozen channels below. Titan's surface is therefore not merely cold. It is chemically active. The atmosphere continually produces organic material, and the landscape continually moves some of that material through wind, rain, erosion, and seasonal change. Dragonfly will arrive in a world where chemistry has been unfolding across the surface for far longer than any laboratory experiment could continue. The first close views came from the Voyager spacecraft. Voyager 1 passed Titan in 1980, approaching closely enough to examine its atmosphere. The encounter confirmed a dense nitrogen-rich envelope, but visible light cameras still could not reveal the ground. Titan appeared as a smooth orange sphere, its secrets remaining below the haze the next. Great effort began with Cassini. Launched in 1997, the Cassini spacecraft traveled for nearly 7 years before entering orbit around Saturn. It carried radar and infrared instruments capable of seeing Titan in ways the human eye could not. During repeated flybys, Cassini gradually assembled maps of a world that had never been visible as a complete landscape. Dark dunes crossed the equatorial regions. Mountain ridges rose from icy crust. Channels spread through the terrain like river systems. Near the poles, radar images revealed lakes and seas whose surfaces were strikingly smooth. Some were filled mainly with methane. Others contained mixtures of methane and ethane. Their shorelines changed, clouds gathered above them, and observations showed evidence of a working climate shaped by seasons that each last more than 7 Earth years. Cassini also carried a smaller craft built by the European Space Agency. This probe was named Huygens, after the astronomer who had discovered Titan more than 3 centuries earlier. In January of 2005, Huygens entered Titan's atmosphere. A heat shield protected it during the first violent stage of descent. Parachutes then slowed the probe as it passed downward through the haze. Its instruments sampled the air, measured winds and temperatures, and photographed the landscape emerging beneath it. The images showed bright highlands divided by dark branching channels. Farther below, the surface became flatter. Rounded pieces of water ice rested on the ground like stones along an earthly riverbank. Huygens landed on a floodplain. Its instruments can continue transmitting for more than an hour from the surface. The ground beneath it was firm but not completely rigid, and the surrounding material showed signs of processes involving liquid methane. For the first time, a machine was resting beneath Titan's sky. But Huygens could not travel. It had been designed to descend, land, and make measurements where it happened to arrive. Its brief success showed what the surface was like at one location. Cassini revealed the broader world from above. Between them, they changed Titan from an orange disk into a place with geography. Dragonfly inherits that geography. Its landing region has been chosen partly from Cassini's radar maps. Its instruments build upon the chemical questions raised by Huygens. Its flight system is possible because earlier missions measured the density, temperature, winds, and structure of Titan's atmosphere. Every planned movement across the surface rests on knowledge gathered by machines that could not make that movement themselves. Cassini circled overhead. Huygens descended once. Dragonfly will land, study, rise, and land again. The difference is not only mechanical, it changes how Titan can be understood. Instead of comparing distant observations made from orbit, scientists will be able to examine separate environments with the same instruments. A dune field can be studied, then left behind. A patch of flatter ground can be sampled. A crater region can be approached over time. The machine will carry its laboratory across the landscape, and beneath each landing site, Titan will offer another small piece of a world that remained hidden for centuries. Flight on Titan begins with a balance between weight and air. Gravity pulls every object toward the surface, just as it does on Earth. But Titan's pull is much weaker. A machine resting there weighs only about 1/7, as much as the same machine would weigh here, even though its mass remains unchanged. Above it lies an atmosphere denser than Earth's. Together, those conditions create one of the most favorable places for powered flight anywhere in the solar system. The rotors do not need to fight the full weight they would carry on Earth, and each blade can push against a thicker body of air. Dragonfly has been shaped around that advantage. The vehicle carries 8 rotors mounted in 4 pairs. Each pair turns in opposite directions, balancing the twisting force created by the blades. If one rotor system develops a problem, the larger arrangement gives the aircraft ways to maintain control that a simpler design would not have. Its body must serve several roles at once. It is an aircraft while moving through the atmosphere, a lander while resting on the ground, a laboratory while examining samples, and a communications station whenever it sends its findings toward Earth. It must survive interplanetary space, atmospheric entry, impact with unfamiliar terrain, intense cold, and years of repeated flights. There are no repair crews on Titan. Every bearing, cable, motor, computer, and instrument must continue working after a journey measured in billions of kilometers. Parts must endure vibration during launch, radiation during the cruise, and temperatures on the surface low enough to change how ordinary materials behave. Lubricants can thicken, metals contract, batteries lose performance. Electrical components that work comfortably inside an earthly laboratory may become unreliable when exposed to Titan's environment. Dragonfly therefore carries much of its sensitive equipment inside an insulated body, where heat can be retained and distributed. The source of that heat is also the source of the mission's electrical power. Sunlight at Saturn is too weak for a practical solar aircraft of Dragonfly's size and purpose. The haze above Titan reduces the available light further. Instead, the vehicle uses a radioisotope power system, drawing energy from the natural decay of plutonium. This system does not function like a reactor. There is no chain reaction and no turbine. Heat released by radioactive decay is converted into electricity, while additional warmth helps protect the spacecraft from the surrounding cold. Similar power systems have supported missions across the outer solar system, including Voyager, Cassini, and the Curiosity and Perseverance rovers on Mars. The available power is steady but limited. Dragonfly cannot fly continuously. After each journey, it must return to the surface and spend time recharging its batteries. The radioisotope generator supplies energy gradually. The batteries store that energy until enough has accumulated for another flight, another sampling operation, or another period of communication. This creates a natural rhythm for the mission. Resting and charging occupy far more time than flying. The vehicle may spend days examining a landing site, taking measurements, and waiting for stored energy to build. Then, the rotor will turn again, lifting the laboratory above the ground for another short crossing. Titan itself moves through a slower rhythm. One Titan day lasts nearly 16 Earth days. This is also the time the Moon takes to orbit Saturn, because Titan keeps the same face turned toward the planet. Daylight and night each continue for many Earth days, while the Sun makes its gradual passage through the hazy sky. Dragonfly's schedule will be shaped by these long cycles. During daylight, cameras can examine the terrain with the help of the filtered sunlight reaching the surface. The aircraft can study possible routes and compare what it sees with maps prepared from orbit. At night, it may continue scientific measurements while remaining on the ground, using the long interval for charging, data processing, and communication. Flying will require more than power. The vehicle must know where it is. Earth's navigation satellites do not reach Titan. There are no radio beacons, surveyed runways, or magnetic maps prepared by earlier explorers. The landscape seen by Dragonfly will sometimes differ from the broad radar images created by Cassini, whose best maps cannot show every rock, slope, or small patch of rough ground. The aircraft must navigate through vision. Cameras will photograph the terrain below and ahead. Computers will compare patterns between successive images, estimating how quickly the ground is moving beneath the vehicle and in which direction. Inertial sensors will track rotation and acceleration. Altimeters will measure the distance to the surface. These systems allow the vehicle to build a local understanding of its surroundings. Before a major flight, Dragonfly can first perform a shorter reconnaissance movement. It may rise, inspect nearby terrain, and return to the same general area. Images collected during that flight can then be sent to Earth, where mission planners study possible routes and landing zones. Commands for the next journey will arrive later. Because Titan is so distant, no person can steer the aircraft as events unfold. A command sent from Earth may require more than an hour to reach the Moon. Any reply begins the same long crossing in the opposite direction. By the time engineers receive confirmation that Dragonfly has lifted off, the flight may already be over. The vehicle must handle immediate decisions on its own. It must respond to winds, maintain balance, avoid hazards, and recognize whether a planned landing area is safe. If the ground below appears too steep or uneven, the navigation system must be able to select a better place nearby. Autonomy does not mean independence from the mission team. People on Earth will choose scientific priorities, examine images, design routes, and decide which regions deserve closer study. Dragonfly will carry those plans into an environment where direct control is impossible, making local adjustments while preserving the larger intent. Each flight will be carefully prepared. The aircraft is not designed to wander without purpose. Movement costs energy, introduces mechanical wear, and leaves behind a site that may contain valuable information. A new destination must offer enough scientific value to justify the crossing. Some flights may cover only a short distance. Others may extend for several kilometers, passing over dunes and flatter corridors before reaching a selected landing zone. Over the planned mission, these separate movements may add up to a journey longer than all the distance traveled by the Mars rovers during their first years of exploration. The comparison is not entirely fair to the rovers. A wheeled vehicle must negotiate every obstacle between one location and another. It must climb slopes, turn around rocks, and search for safe paths through loose soil. Dragonfly can rise above many of those barriers. A dune that would block a rover becomes terrain beneath the rotors. A channel does not need to be crossed at ground level. A field of broken ice can be examined from above before the machine chooses a place to descend. Flight also changes perspective. From the surface, Dragonfly's cameras can examine grained stones and local textures. From the air, the same cameras can see how those features fit into a larger pattern. a single landing site becomes part of a dune field, an eroded plain, or an impact structure. The machine will repeatedly shift between those scales. Close inspection will reveal composition, aerial views will reveal geography. The two forms of knowledge can guide one another as the mission moves forward. Before Dragonfly ever reaches Titan, engineers must learn how it will behave in air. No laboratory can reproduce perfectly. Titan's atmosphere is mostly nitrogen, like Earth's, but it is colder and denser. Test facilities can imitate fictions of those conditions, allowing rotor systems and vehicle components to be studied under carefully controlled pressures and temperatures. Other tests take place in ordinary air. Full-scale and smaller aircraft can demonstrate control methods, navigation software, and emergency responses. Engineers can create wind, heat, vibration, and mechanical loads that push the design beyond what it should normally encounter. The purpose is not to prove that nothing can go wrong. It is to discover weaknesses while they can still be corrected. A rotorcraft on Earth can be watched closely. Sensors can record the bending of blades, the temperature of motors, and the movement of the frame. Parts can be removed, inspected, and redesigned. On Titan, the same actions will be impossible. The machine must carry the memory of all those tests within its construction. Its landing legs must tolerate uneven ground. Its rotors must survive repeated cycles of cold and movement. Its computers must recognize conditions their programmers cannot fully predict. Its sampling tools must reach beneath the surface without making the aircraft unstable. Even dust matters. Titan's dunes contain fine organic particles that may cling to surfaces, enter mechanisms, or behave differently under the moon's low gravity. Rotor wash may lift some of this material during takeoff and landing. Engineers must consider how the moving air will disturb the ground and whether it could affect cameras, instruments, or later chemical measurements. For that reason, Dragonfly's sampling system will not simply scoop whatever lies beside its landing gear. Small drills mounted near the skids will collect material from the surface and shallow subsurface. Pneumatic lines will carry selected particles into the interior of the laboratory, where instruments can separate and examine their molecules. The aircraft may sample one site, fly away, and then study a chemically different region with the same equipment. This mobility is central to the mission. Titan is not one environment repeated across an entire moon. Its equatorial dunes contain processed organic material. The flatter ground between them may expose water ice or mixtures altered by past weather. Impact craters may preserve evidence of heating and temporary liquid water. No single landing place can represent all of this. Dragonfly's rotors turn a fixed laboratory into a traveling comparison. The first flights will likely be cautious. The aircraft will learn how Titan's real atmosphere differs from predictions. It will measure wind near the surface, watch how the ground responds to rotor wash, and test its ability to rise, hover, move, and land. Each successful movement will enlarge the region that can be explored. The horizon from one landing site may contain the destination of a later flight. Beyond that destination will be another line of terrain, and beyond it another, all beneath the same orange atmosphere. The machine will not cross Titan quickly. It will move in measured stages, carrying stored energy and accumulated knowledge from one piece of ground to the next. And for the first time, a laboratory from Earth will learn another world by flying through its air. Beneath Dragonfly's protective shell, the mission carries a group of instruments designed to answer different versions of the same question. What has Titan's chemistry been able to build? The moon begins with simple materials. Nitrogen dominates the atmosphere. Methane supplies carbon and hydrogen. Sunlight and energetic particles break those molecules apart high above the surface, allowing their fragments to combine into larger forms. The products descend through the haze. Some remain in the air as gases. Some become tiny solid particles. Others settle onto the landscape and enter dunes, plains, channels, and craters. Over millions of years, Titan has collected an immense natural archive of carbon chemistry. Dragonfly will search through that archive one landing site at a time. Its most detailed chemical work will be performed by the Dragonfly mass spectrometer, known as DRAMs. A mass spectrometer does not identify material by looking at its color or shape. It begins by taking molecules apart in a controlled way. The resulting charged fragments are separated according to their mass and electrical behavior, creating a pattern that scientists can use to infer what the original sample contained. On Earth, instruments based on this principle work in hospitals, environmental laboratories, geological surveys, and studies of living cells. They can distinguish substances that appear nearly identical from the outside because their internal molecular structures produce different signatures. On Titan, DRAMs will examine grains delivered from the surface. Dragonfly's sampling drills are mounted near its landing skids. After the aircraft settles, one of these tools can grind into the nearby material. The loosened particles are carried through narrow tubes by a stream of gas and delivered into the body of the vehicle. This arrangement keeps the central laboratory protected. The drill reaches outward, while the sensitive instruments remain inside a warmer, cleaner compartment. Two sampling systems provide redundancy and also allow material to be gathered from more than one side of the aircraft. Not every grain will be treated in the same way. Some samples may be heated so that volatile compounds escape as gas. Others may be exposed to chemical preparation methods that make certain complex molecules easier to detect. DRAMs can then measure the fragments and search for patterns as associated with carbon-rich compounds, nitrogen-bearing molecules, and substances relevant to prebiotic chemistry. Prebiotic does not mean alive. It describes chemistry that can occur before biology begins, including reactions that form increasingly complex organic molecules. Some of these compounds can become parts of living systems under the right conditions, but their presence alone would not show that life exists or ever existed. This distinction matters on Titan. Organic material is abundant there because carbon chemistry takes place throughout the atmosphere. The discovery of complex molecules would therefore be expected in a broad sense. The deeper questions concern which molecules have formed, how they are distributed, and whether different environments have changed them in different ways. A grain from an equatorial dune may have spent a long time exposed to atmospheric products and surface radiation. Material near an impact crater may have encountered heat or liquid water. A patch of icy ground between dunes may preserve another chemical history. By moving between these places, Dragonfly can compare molecular patterns rather than interpreting a single sample in isolation. DRAMs will look closely at those patterns, including the structures of molecules that share the same ingredients but arrange their atoms differently. This isomerism can matter in chemistry. Two molecules may contain equal numbers of carbon, hydrogen, nitrogen, and oxygen atoms while behaving differently because those atoms are connected in another order. In biological systems on Earth, shape and arrangement often determine whether a molecule can participate in a particular process. Titan offers a chance to study how far such complexity may develop without the active surface biosphere found on our planet. Another instrument will examine the ground without first bringing it inside. The Dragonfly Gamma Ray and Neutron Spectrometer, or DRAGON-S, will investigate the elemental composition beneath and around the lander. Cosmic rays and natural radioactive processes can produce neutrons in planetary surfaces. As those neutrons move through nearby material, they lose energy and interact with atomic nuclei. Some interactions release gamma rays with energies characteristic of particular elements. By measuring these signals, DRAGON-S can estimate which elements are present. Hydrogen is especially important because it can help reveal materials containing water ice or hydrocarbons. Carbon, nitrogen, oxygen, and other elements provide additional clues about the composition of a landing site and the processes that shaped it. The instrument can survey a broader volume than the drill alone. Before Dragonfly collects a sample, DRAGON-S may help indicate whether the ground beneath one side of the aircraft differs from another region nearby. It can also place the small drilled sample within a larger chemical setting. A few particles entering the laboratory cannot describe an entire dune. A measurement extending into the surrounding ground can show whether those particles are typical of the site or belong to a narrow patch. Dragonfly will also carry a suite called Dragomet, devoted to geophysics and meteorology. Titan has weather, but very few direct measurements have ever been made from its surface. Huygens recorded conditions during its descent and brief operation on the ground. Cassini watched clouds and seasonal changes from orbit. Dragonfly will remain within the lower atmosphere for years. It will measure temperature, pressure, wind, and the changing behavior of the air. These readings will help engineers operate the vehicle, but they also belong to a larger study of Titan's climate. Near-surface winds shape dunes and transport organic grains. Humidity measurements can reveal the presence and movement of methane vapor. Pressure changes may reflect weather systems passing through the region. The atmosphere may seem calm during many observations. Titan receives less solar energy than Earth, and its weather unfolds within long seasonal cycles. But calm does not mean motionless. Winds continue to reshape the equatorial landscape. Methane can evaporate, condense, and fall as rain. Clouds can gather and disappear over spans of time that Dragonfly may be able to observe directly. The vehicle's instruments will experience this atmosphere, both while resting and while flying. During a flight, changes in wind and air density become part of navigation. After landing, the same conditions become scientific measurements. The aircraft itself acts as a moving weather station, carrying calibrated sensors across different elevations and terrains. Dragmet also includes sensors that will listen to the ground. Titan's interior is hidden beneath a crust dominated by water ice. Evidence from Cassini has long supported the possibility of liquid water at depth, though newer interpretations suggest the internal structure may be more complicated than a simple global ocean beneath a uniform shell. A seismometer cannot see through the crust directly. It listens for movement. Impacts, cracking ice, tidal flexing, or other internal processes can send vibrations through the ground. The way those vibrations travel depends on the materials they cross. Solid ice, porous deposits, and liquid layers transmit seismic energy differently. Dragonfly may remain still for long periods while its seismometer waits. The rotors will be silent. Sampling tools will be inactive. Within the surrounding ground, faint vibrations may pass beneath the landing legs. Some may come from the local settling of material. Others could arrive from far across the moon. A single station cannot map an interior as completely as a global network could. Yet repeated measurements from multiple landing sites may reveal whether Titan is seismically active and how its shallow crust varies from place to place. Even the absence of detectable events can place limits on certain kinds of activity. The Dragonfly camera suite, called DragonCam, will provide the mission's visual record. Its cameras will serve scientific, navigational, and operational roles. Some will survey broad terrain. Others will inspect the surface in greater detail. Images will help the team select sampling locations, study geological structures, and reconstruct the shape of the route already traveled. Titan's daylight is dim, and its haze changes the spectrum of the light reaching the ground. DragonCam therefore cannot rely only on ordinary photography. The suite includes illumination systems that allow nearby surfaces to be examined under controlled light, including wavelengths chosen to reveal details that might be difficult to distinguish beneath the natural orange sky. A dune grain may appear dark from a distance. Under closer inspection, its texture, layering, and relationship to surrounding ice can become more informative. Images of drill sites will show how the ground responds when disturbed. Views beneath and around the lander will help connect laboratory chemistry with visible geology. From the air, DragonCam will widen the scene. Dune crests will form long parallel lines beneath the vehicle. Interdune corridors may expose brighter material. Channels, ridges, and impact features can be photographed from angles Cassini could never obtain. These aerial images will not resemble photographs from a high satellite orbit. Dragonfly will fly close to the terrain. Its view may carry the intimacy of an aircraft crossing above a remote desert, with details changing gradually below and the horizon muted by haze. The mission's final major instrument is called Dragonfly Geophysics and Meteorology only in part because the scientific systems overlap in purpose. Cameras support geology, weather sensors support flight. Chemical instruments help interpret the history of the terrain. No measurement stands entirely alone. A temperature reading changes how a chemical result is understood. An image explains where a sample came from. An elemental survey guides the drill. A seismic measurement adds depth beneath the visible ground. The instruments become most useful when their findings are combined. Suppose Dragonfly lands in a bright patch between dark dunes. The cameras first record the site, revealing the shape and texture of the surface. Dragon-S measures the elemental composition beneath the vehicle and suggests that the ground contains more water ice than the nearby dune material. The drill collects a sample. DRAMS examines its molecules and finds a mixture different from those measured at an earlier landing site. Weather sensors record the local air, while the seismometer listens to the mechanical response of the ground. From these separate observations, scientists can begin to reconstruct a history. Perhaps water-rich crust was exposed by erosion. Perhaps organic particles accumulated there after being carried by wind. Perhaps the chemistry was altered by a past event that briefly warmed the surface. Each explanation must be tested against the complete set of measurements. Dragonfly is not built around a single detector that will announce one decisive answer. Its strength comes from comparison, repetition, and context. The same instrument will examine different terrains. The same terrain will be examined in different ways. Results that appear interesting at one site can be tested again somewhere else. This is how a moving laboratory turns geography into an experiment. Titan has already carried out the chemistry. Its atmosphere produced the raw material. Its weather moved that material. Its impacts, seasons, and surface processes altered it over time. Dragonfly will arrive much later, carrying tools small enough to fit within one aircraft and sensitive enough to read traces of that long history. At each landing site, the rotors will stop, the instruments will awaken, and a few grains from beneath the orange sky will enter a laboratory built on another world. Dragonfly's first home on Titan will be a landscape shaped by wind. Across the moon's equatorial regions, dark dunes extend for hundreds of kilometers. In radar images from Cassini, they appear as long parallel bands, often wrapping around brighter highlands and separating into broad corridors where the underlying ground becomes visible. From orbit, the pattern resembles a desert. But Titan's dunes are not built from the same kind of sand found in most deserts on Earth. Their grains are not primarily quartz worn from mountains by water and time. They are thought to contain carbon-rich material created in the atmosphere, carried downward through the haze, altered on the surface, and gathered by wind into enormous fields. The particles may begin as very small aerosols. High above Titan, ultraviolet light and energetic particles break apart methane and nitrogen. The fragments combine into increasingly complicated molecules. Some become gases. Others grow into solid particles that descend through the atmosphere over long periods. By the time they reach the ground, they have passed through layers of temperature, pressure, and chemistry. They may settle as fine material too small to form dunes immediately. To become mobile grains, the particles must grow, clump together, or be reshaped by processes near the surface. Exactly how this happens remains one of Titan's open questions. On Earth, a grain of sand can be examined in the hand. Its edges reveal whether it was recently broken from rock or carried far by wind. Its mineral structure can show where it formed. Its surface may preserve tiny marks left by collisions with other grains. Titan's dune particles may hold a different kind of history. Their chemistry begins in the sky. Their final shape may be produced on the ground. Between those stages lies a sequence that no spacecraft has yet observed directly. Dragonfly will enter this sequence near its end. Its planned landing region lies within the Shangri-La dune field, close to Titan's equator. The name was assigned to a broad, dark region seen in early maps before its detailed nature was understood. Cassini later revealed the long dune forms crossing much of the area. These dunes are immense in scale. Individual ridges may rise tens of meters above the surrounding terrain and continue for many kilometers. The spaces between them can be wide enough to contain flatter surfaces, exposed ice-rich material, or deposits with a different chemical history. Dragonfly is expected to land within one of these interdune regions rather than directly on a steep ridge. The flatter ground provides a safer beginning. It also places the vehicle beside two contrasting environments. One lies in the dark dune material, the other lies in the brighter terrain between the ridges. A short flight may be enough to move from one to the other. That simple crossing could become the mission's first major comparison. The dark grains may be rich in complex atmospheric organics. The brighter ground may contain more water ice or material exposed from beneath the surface. If their compositions differ, Dragonfly's instruments can begin to trace how Titan sorts, transports, and transforms it into mystery. The dunes themselves record the movement of the atmosphere. Wind pushes grains across a surface when the force of the moving air becomes strong enough to overcome gravity, friction, and the tendency of particles to cling together. Titan's low gravity makes lifting easier, but the nature of the grains may make movement more complicated. Organic particles can be softer than mineral sand. They may carry electrical charges. They may stick after contact. The cold may change their mechanical behavior, and liquid methane may sometimes wet the surface or alter the bonds between grains. A particle that appears light out enough to move easily may still resist the wind because it is attached to its neighbors. Researchers study these possibilities using laboratory materials intended to imitate Titan's organic solids. No substitute is perfect. The real particles have been produced by chemistry unfolding in Titan's atmosphere, under conditions that cannot be recreated completely on Earth. Their shapes, strength, porosity, and surface properties remain uncertain. Dragonfly will encounter the grains as they are. Cameras can examine their appearance. Sampling tools can test how the ground responds when drilled. The mass spectrometer can investigate molecular composition. Measurements during landing and takeoff may reveal how easily the material is disturbed by rotor wash. Even the marks left by the aircraft may become useful. When the rotors accelerate, they will force air downward. That air will spread across the surface, carrying loose particles away from the landing legs. Cameras may observe whether the ground darkens, brightens, or develops small patterns as the upper layer is disturbed. A resistant surface would suggest that grains are bonded or compacted. A rapidly moving cloud of particles would indicate looser material. The effects must be managed carefully because the same rotor wash that reveals physical behavior can also alter a future sampling area. Mission planners will need to distinguish material exposed naturally from material rearranged by the spacecraft itself. Titan's winds have already performed their own sorting. Long dunes tend to align with the direction of the winds that build them, but Titan's atmospheric circulation is not simple. Near the surface, common winds may move gently in one direction, while rarer, stronger events push material another way. Storms may play a disproportionate role. Methane clouds can gather near the equator during certain seasons. Rain may fall across dry terrain, darkening broad areas and forming temporary flows. Gust fronts associated with these storms could produce winds strong enough to move large amounts of dune material. A landscape can therefore preserve the influence of events that happen only occasionally. Most days may pass with little visible change. Then a storm arrives, and the work of many quiet months is compressed into a short period of movement. The orientation of Titan's dunes suggests that these rare atmospheric events may help shape their long-term direction. Dragonfly's mission will cover only a small part of one Titan season, so it may not witness every kind of weather responsible for the landscape around it. Still, local measurements can test the models. Wind direction near the ground can be compared with the alignment of nearby ridges. Pressure and temperature changes can reveal passing weather systems. Images taken over time may show whether grains shift between visits. A dune field is not a frozen structure. It is a record that continues to be written. On Earth, deserts can appear empty from a distance, yet close inspection reveals layers of motion. Grains leap and roll. Fine dust travels far above the surface. Ridges migrate. Small slopes collapse when they become too steep. Titan's dunes may share some of these behaviors, but at a different pace and within a different material world. The sunlight is weaker, the gravity is lower, the atmosphere is thicker. The grains may be organic rather than mineral. The liquid that sometimes falls from clouds is methane rather than water. These differences turn a familiar landform into a new experiment in planetary physics. The dunes also connect the atmosphere to the surface. A molecule formed high above Titan can eventually become part of a grain. That grain may descend, join other material, move across the equator, and accumulate within a ridge. Later, wind may uncover it again. Rain may carry it into a channel. An impact may heat it. A sampling drill may finally bring it into Dragonfly's laboratory. The path from upper atmosphere to instrument tray could take millions of years. The molecule does not preserve every stage clearly. Chemical bonds can break and reform. Radiation can alter exposed material. Contact with other substances can create new products. But the final sample still carries evidence of its journey. Its elemental composition reveals ingredients. Its molecular structures reveal some of the reactions that occurred. Its location within a dune, corridor, or crater gives geological context. Dragonfly's mobility allows these clues to be compared across distance. The first samples may come from material that has been heavily processed by the atmosphere and wind. Later sites may include deposits with stronger evidence of water ice, and farther along the planned route, the influence of an impact crater may introduce another layer of chemical history. The mission is designed to move from one kind of question toward another. At the dunes, the focus begins with atmospheric organic material. What reaches the ground? How are the particles assembled? How does wind transport them? How chemically complex have they become? These questions do not require life to be present. They concern the natural capacity of an atmosphere to build complexity from simple molecules. Titan provides a planetary laboratory where this process has continued on a global scale, largely separated from the oxygen-rich environment and biological recycling that continually reshape organic material on Earth. Our planet does not preserve a clean record of its earliest surface chemistry. Plate tectonics has recycled crust. Water has eroded ancient landscapes. Living organisms have transformed the atmosphere, oceans, soil. The molecules, as present today, exist within a world thoroughly altered by life. Titan offers no exact copy of the young Earth. Its temperature is far lower. Its surface liquids are hydrocarbons. Its atmosphere and geology follow their own history. Yet some of the chemical ingredients and energy sources resemble processes that may have mattered before biology changed our planet. This makes comparison valuable, but it must remain careful. Titan is not a preserved version of Earth's past. It is a separate world that demonstrating what carbon chemistry can do under another set of conditions. Dragonfly will not search for a single substance that completes the story. Prebiotic chemistry is not a straight ladder in which each new molecule leads inevitably toward life. It is a network of possible reactions, many of which end without producing anything biological. Complexity alone is not destiny. An atmosphere may create elaborate organics that remain chemically interesting, but never become part of a self-sustaining system. A temporary pool of liquid water may support reactions without leading farther. Molecules can form, break apart, and vanish. The mission will study possibility rather than inevitability. In the dune fields, that possibility is spread across the ground. A dark ridge contains particles made from countless atmospheric reactions. Each grain is small, but the full landscape represents an enormous accumulated mass of organic material. From above, Dragonfly may see dune after dune extending toward the hazy horizon. The scale can be difficult to hold in mind. A laboratory on Earth might produce a thin film of Titan-like material inside a chamber. Titan's atmosphere has been producing related substances across an entire moon for geological spans of time. The dunes are chemistry made visible as geography. Their ridges show where wind has placed the products. Their color distinguishes them from water ice or terrain. Their shape records the circulation of the air. Their grains preserve some fraction of the reactions that began far overhead. Dragonfly will move through this landscape in short stages. After landing, it may remain in one area for several Titan days. The aircraft will photograph the surroundings, examine the ground, and send its findings across space. Scientists will study the data and decide which nearby feature offers the strongest next step. A ridge may be approached from a safer slope. An interdune patch may be sampled before the vehicle crosses into darker material. A flight path may follow a broad corridor where landing options remain visible beneath the aircraft. Progress will be deliberate because every location can add context to the previous one. At one site, the drill may encounter loose grains. At another, the surface may be crusted or compacted. A third may contain a mixture of organic particles and exposed ice. Differences that appear minor in images may become significant in the laboratory. The chemistry of a dune can change with depth. The uppermost grains receive more exposure to radiation and atmospheric exchange. Material below may be less altered. A shallow drill cannot reach deeply into Titan's crust, but even a small difference beneath the surface can help reveal how quickly chemical processing occurs. Repeated sampling may show whether the dune material is uniform. If similar molecular patterns appear across many sites, the atmospheric production process may dominate. If strong local variations emerge, then surface conditions, transport history, or contact with other materials may matter more than expected. Dragonfly will also carry the memory of its route. Each set of images, spectra, weather readings, and chemical measurements will be tied to a location. Over time, the mission can build a connected record rather than a collection of isolated results. The first landing site becomes the reference. The next site introduces a difference. The third helps show whether that difference belongs to a larger pattern. A flight across Titan is therefore not only transportation, it is the line joining one experiment to another. Outside the vehicle, the dunes will remain exposed to the weak sunlight and the movement of the air. Their ridges may change too slowly for a human eye to notice, yet grain by grain, they continue to travel. Some particles may have crossed great distances before Dragonfly arrives. Others may have remained buried for ages within a single ridge. The aircraft will touch down among them briefly, take a small sample, and leave again. Behind it, the atmosphere will continue shaping the same dark landscape. Ahead, the route will begin to turn toward older and more complicated ground. Beyond the equatorial dunes, the ground begins to carry the memory of impact. Dragonfly's route leads towards Selk crater, a broad, circular structure roughly 50 miles across. From the surface, its full shape will not be visible at once. The horizon lies too near, and Titan's haze limits distant views. The crater will emerge gradually through changes in elevation, exposed materials, broken terrain, and the widening evidence of an event that occurred long before the aircraft arrived. An object once struck Titan there. It may have been an asteroid or a comet, moving far faster than any storm wind, and carrying enough energy to reshape a large region of the icy crust. In moments, the impact compressed, fractured, heated, and displaced material that had remained cold for ages. The initial excavation would have been violent. A cavity opened in the surface. Water ice behaved briefly like shattered rock. Material rose along the crater rim and fell back across the surrounding landscape. Beneath the impact point, heat spread through the damaged crust. The event ended quickly. Its chemical consequences may have continued much longer. At Titan's usual surface temperature, water is locked into hard ice. It cannot flow through channels or gather in exposed pools as it does on Earth. Yet a large impact can supply enough heat to melt part of that frozen crust. For a time, Selk may have contained liquid water. The melt could have collected in the crater floor, mixed with broken ice, or remained within pockets beneath insulating debris. Models differ on the amount of water produced and the length of time it persisted. Depending on the depth, composition, and distribution of the heated material, some liquid environments may have lasted for hundreds, thousands, or perhaps longer spans before freezing again. That uncertainty is part of the reason Dragonfly is going there. The dunes provide organic material made largely through atmospheric chemistry. Selk crater may preserve places where similar carbon-rich material encountered liquid water. Neither ingredient is rare in the solar system when considered separately. Water ice covers moons and distant worlds. Organic molecules occur in meteorites, comets, planetary atmospheres, and interstellar clouds. The more revealing conditions appear when these materials come together in an environment with enough energy for reactions to proceed. A molecule suspended in a cold hydrocarbon grain may remain unchanged for a long time. Place the molecule in liquid water and new possibilities appear. Water can dissolve substances that bring different molecules into contact, carry ions, support reactions, and allow products to move away from the place where they formed. It is not a guarantee of biological chemistry. It is a medium through which chemical pathways can become broader and more connected. At Selk, that medium may once have existed beneath the orange atmosphere. The impact would not have created an earthly lake in any familiar sense. The water may have contained ammonia and other compounds that lowered its freezing point. It may have been cloudy with pulverized ice and rock-like material. Organic grains falling from the atmosphere could have entered from above or been mixed into the crater during the impact itself. The environment would have changed continuously as it cooled. Warm liquid near the center might have remained mobile while outer regions froze. Dissolved compounds could have concentrated along the advancing boundaries of ice. Minerals and organic substances may have settled at different rates. Reactions favored at one temperature could have slowed as the water became colder. Eventually, the surface returned to Titan's usual state. The liquid disappeared from view. Its products, if any formed, may remain inside frozen deposits, altered sediments, or material later exposed by erosion. Wind and methane weather may have reworked the crater floor. Organic particles from the atmosphere continued to settle long after the impact. Dragonfly will arrive after all of this. It will not witness the warm stage. It will search for chemical and geological traces left behind. The route towards Selk creates a progression across Titan's history. At the first landing sites, the aircraft will examine landscapes dominated by atmosphere and wind. The organic grains there may represent long exposure to methane, nitrogen, sunlight, and energetic particles. Closer to the crater, the materials may reflect impact heating, broken crust, and contact between substances that usually remain separated. The same instruments can examine both settings. This matters because a complex molecule found near Selk would be difficult to interpret without comparison. Titan's atmosphere can produce complicated organic chemistry on its own. Some substances that appear significant may already be common across the dune fields. A difference between environments carries more meaning than a single detection. Suppose one molecular family appears throughout the dunes, but is absent near the crater. That absence may indicate destruction by heat, water, or later alteration. Suppose another group becomes more abundant in water-rich material. That pattern could suggest that liquid water supported reactions not favored in the dry organic deposits. Suppose the samples show no meaningful difference at all. That result would also matter. It could indicate that the warm environment was too brief, that later processes erased its record, or that the expected chemical pathways did not occur under Titan's conditions. Science at Selk will not depend on finding a preferred answer. The crater is valuable because it allows competing possibilities to meet the same measurements. Dragonfly will look for molecules with structures relevant to the chemistry of life, including compounds that contain carbon, hydrogen, oxygen, and nitrogen in arrangements capable of further reaction. It may examine whether molecules occur in repeating families, whether their shapes show signs of chemical selection, and whether water-altered material differs from material processed only in the atmosphere. These measurements require restraint in interpretation. Amino acids, for example, are often associated with living organisms because life on Earth uses them to build proteins. Yet, amino acids can also form without biology. They have been found in meteorites and produced in laboratory experiments that contain no living cells. their presence on Titan would be scientifically important. It would not by itself be evidence of life. The same caution applies to other complex organic compounds. Chemistry can create patterns that appear organized. Some reactions favor particular products over others. Crystals can sort molecules. Cycles of freezing and thawing can concentrate substances. Energy flowing through a system can build structure without producing anything alive. Dragonfly's task is to measure how far these non-living processes have gone. This question reaches beyond Titan. Before life appeared on Earth, our planet also contained water, carbon-bearing compounds, minerals, atmospheric gases, and many forms of energy. Somehow, within that environment, chemistry crossed into systems capable of storing information, using energy, maintaining boundaries, and reproducing with variation. The details remain incomplete. Earth has not preserved an untouched record of the transition. The oldest rocks have been heated, buried, fractured, and recycled. Later life entered nearly every accessible environment, changing the chemistry that came before it. Titan does not offer a direct reconstruction of that early Earth. The Moon is much colder. Its atmosphere contains almost no free oxygen. Methane and ethane play the surface role that liquid water plays here. Its crust, gravity, sunlight, and geological history are different. Yet those differences make Titan useful. They provide another natural experiment. The same elements can be placed under unfamiliar conditions. Organic material can accumulate without forests, oceans of liquid water, or an active biosphere constantly consuming and rebuilding it. Temporary water can interact with that material and then freeze, preserving a chemical moment that Earth may have erased. Selk crater may be one such moment. The crater is not perfectly preserved. Titan's atmosphere protects the surface from many small impacts, but weather and sediment continue to alter what remains. Methane rain can erode slopes. Wind can deposit dune material. Organic haze settles everywhere. The features visible today represent both the original impact and everything that happened afterward. Dragonfly's cameras will help separate these histories. Layers exposed along slopes may reveal different materials. Blocks of water ice may stand out from darker deposits. Channels may show where liquid methane moved through the crater region. Variations in texture can guide the aircraft toward places where subsurface material is more accessible. The rotorcraft will not need to reach the crater's exact center to learn from the impact. Ejected material may lie beyond the rim. Fractured deposits can expose deeper crust. Melt products may have been redistributed across the floor and surrounding terrain. Each location offers a different part of the event. The aircraft can approach gradually, testing the ground before committing to more difficult areas. A reconnaissance flight may reveal slopes hidden in radar maps. Nearby landing zones can be compared for safety and scientific value. The route will depend partly on what Dragonfly discovers along the way. Mission planning begins with maps and models, but Titan will provide the final terrain. A region that appears uniform from orbit may contain unexpected exposures. A promising landing zone may prove too rough. A minor feature may reveal a composition that changes the priorities of later flights. The locked destination is not a single point. It is a scientific region with many possible paths through it. As Dragonfly travels, the crater may first appear indirectly. The composition of the ground may shift. Water ice may become more abundant. The orientation of ridges may change. Fragments excavated by the impact may lie among younger deposits. Only after several flights might the larger structure begin to take form in the mission's images. This gradual approach mirrors the way planetary landscapes are often understood. A crater seen from orbit is a circle. A crater explored from the ground is a sequence of slopes, grains, blocks, layers, and chemical boundaries. Its global shape explains where the machine is. Its local details explain what happened. Dragonfly will move between those scales. From the air, cameras will map connections across the terrain. On the ground, instruments will study a few centimeters of material with great care. The crater's age remains uncertain. Titan's surface does not carry enough clearly preserved impacts to make dating simple. On worlds such as the Moon, Scientists can estimate the age of terrain by counting craters. Older surfaces generally accumulate more of them. Titan's atmosphere screens out smaller incoming objects, while weather and geology erase or bury some structures that do form. Selk belongs to a history that cannot yet be placed precisely on a calendar. It may have formed hundreds of millions of years ago. Its present condition depends not only on age but on erosion, burial, and the movement of organic material across the region. Dragonfly may help refine that history. The sharpness of slopes, the depth of sediment, and the composition of exposed deposits can place limits on how the crater evolved. Weather measurements can show which processes remain active now. Seismic observations may reveal fractures beneath the landing sites. A crater is not only a scar on the surface, it is a temporary opening into the interior. The impact excavated material from below and placed it within reach of instruments arriving much later. Substances normally buried beneath Titan's organic coating may now lie closer to the surface. Water ice is one of those substances. Titan's outer crust is largely made from it, but atmospheric products can cover the ground with darker carbon-rich material. At Selk, broken and uplifted ice may create natural exposures where Dragonfly can investigate the relationship between the moon's crust and the chemistry descending from the sky. Ammonia may also be important. Mixed with water, it can allow liquid to remain stable at lower temperatures. Evidence for ammonia-bearing material could change estimates of how long impact melt persisted. It could also influence which chemical reactions were possible. Other salts or compounds may have altered the water as well. The liquid environment, if present, would not have been chemically pure. It would have drawn ingredients from the impactor, Titan's crust, the atmosphere, and surface deposits accumulated before the collision. Every source adds uncertainty. It also adds possibility. The impactor may have carried its own organic molecules. The crust may have contributed minerals or compounds capable of helping reactions. The atmosphere supplied a long history of carbon-rich particles. Heat brought these materials into contact, then cooling preserved part of the result. Dragonfly's mass spectrometer can search for that result, but preservation will determine what remains detectable. Some molecules break down under radiation. Others react with the atmosphere. Methane rain may transport soluble substances away from their original location. Burial can protect material. A thin layer of sediment may shield molecules from surface radiation and chemical weathering. The drills cannot reach far underground, yet a freshly exposed slope or disturbed deposit may bring protected material within range. Choosing the right sampling site, therefore, requires geology as much as chemistry. An instrument can analyze only what enters it. The cameras must first identify the setting. Elemental measurements must describe the surrounding ground. The drill must reach material that represents the feature of interest, rather than a coating deposited later. One landing may not resolve the question. Dragonfly can sample again. The ability to repeat a measurement in another location is among the mission's strongest tools. A surprising result at one site may be contamination, local variation, or an instrument effect. Finding a related pattern elsewhere makes the interpretation stronger. Mobility turns uncertainty into a route. The aircraft can leave one explanation behind and fly toward another test. At Selk, the most important comparisons may occur across boundaries. Dark organic deposits beside brighter ice, crater ejecta beside later sediments, raised terrain beside lower regions where liquids may once have collected, materials exposed to the atmosphere beside grains sheltered below the surface. Chemical changes often become easiest to recognize where one environment meets another. A boundary can preserve movement from one state into the next. The impact itself created a boundary in time. Before it, the region was part of Titan's cold crust, receiving organic material from above. During the collision, temperature and pressure changed abruptly. Afterward, the crater cooled and entered the long processes of weathering and burial. Dragonfly will look for where these stages remain written into the ground. The mission's interest in habitability belongs within this history. A habitable environment is one capable of supporting life as we understand it, at least for some period. It does not follow that life occupied it. A warm pool may contain useful chemistry without ever developing a living system. At Selk, even habitability may have been limited. The liquid water could have been too cold, too brief, too chemically unbalanced, or too isolated. Essential ingredients may not have been available in useful forms. Energy sources may have faded before complex reactions progressed. The crater provides an opportunity, not a promise. Dragonfly will measure the conditions that can still be reconstructed. It will ask whether water and organics truly mixed, what products formed, and whether the environment supported increasing chemical complexity. This approach protects the mission from a misleading expectation. There may be no single moment when an instrument finds the answer. Instead, evidence will accumulate across measurements. A sample shows certain molecules. A nearby elemental survey confirms water-rich material. Images place the sample within an impact deposit. Another landing reveals a related pattern. Laboratory teams on Earth compare the data with experiments and models. Months or years may pass before the full meaning becomes clear. The most important discovery could be a relationship rather than an object. Perhaps water exposure favors one group of compounds. Perhaps Titan's atmospheric organics prove more reactive than expected. Perhaps impact heating destroys complexity before it can progress. Perhaps the crater contains several chemical histories layered together. Each possibility teaches something about the path from simple ingredients toward organized chemistry. Long before Dragonfly arrives, scientists can explore parts of these questions in laboratories. They create Titan-like gases and expose them to energy, producing hazy organic material. They mix those products with water, ammonia, or ice, heat, freeze, irradiate, and analyze the results. These experiments show what can happen under selected conditions. Titan shows what did happen within a planetary environment. The difference is large. A laboratory chamber runs for days, months, or occasionally longer. Titan's atmosphere has processed methane and nitrogen across geological time. A small sample in a sealed vessel cannot reproduce changing seasons, impacts, sediment transport, burial, or the enormous variety of local conditions across a moon. Dragonfly connects the controlled experiment to the natural one. The molecules it detects can be recreated and tested on Earth. Researchers can ask what pathways produce them, which environments preserve them, and whether the observed mixtures require water or can arise without it. The process moves back and forth. Titan guides the laboratory. The laboratory helps interpret Titan. This exchange may continue long after the nominal mission ends. Data returned from the crater will be archived for future researchers, using analytical methods that have not yet been developed. A spectrum that appears confusing at first may become understandable when new experiments reveal how a molecule fragments. A geological pattern may gain meaning when later missions improve the map of Titan's interior or climate. Dragonfly's physical journey will last a few years on the surface. Its scientific journey can extend much longer. The samples themselves will remain on Titan. The mission is not designed to bring material back to Earth. Every conclusion must come from instruments carried inside the rotorcraft and from the signals transmitted home. This places great importance on calibration. Before launch, scientists expose the instruments to known substances and record how they respond. They test mixtures, temperature ranges, and possible contaminants from the spacecraft. They build a library of patterns that can be compared with future measurements. After landing, internal standards help track whether the instruments continue to behave as expected. Blank measurements can show whether material remains from an earlier sample. Repeated analysis can separate a true Titan signal from something introduced during construction or flight. The cleanest interpretation depends on knowing the machine almost as carefully as the moon. Even then, ambiguity will remain. Complex chemistry rarely produces one unmistakable signature. Molecules can fragment in similar ways. A sample may contain thousands of compounds overlapping within the same measurement. Scientists will use several techniques to narrow the possibilities. The uncertainty will not be a flaw in the mission. It is part of studying matter at the edge of what instruments can resolve. Dragonfly is designed to reduce that uncertainty step by step. The route from the dunes to Selk is therefore more than a change in scenery. It is a movement between chemical regimes. The first is shaped mainly by the atmosphere. The second may preserve the influence of liquid water. Between them lie terrains where the two histories overlap in different proportions. The aircraft can follow that gradient across the surface. At each stop, the distinction may become clearer or more complicated. Organic material will not disappear as Dragonfly approaches the crater. It continues to fall from the atmosphere everywhere on Titan. Younger deposits may cover older water-altered material. Dunes may have migrated into the crater. Methane rain may have carried particles across boundaries. The mission must look beneath the newest layer where possible. A shallow exposure can be enough. An eroded slope may reveal older deposits. A small impact may excavate material from below. The edge of a block may preserve a surface protected from later sediment. DragonCam can search for these openings, while compositional instruments determine whether they differ from the surrounding ground. Flying over Selk may reveal patterns impossible to recognize from a single landing site. Channels may converge toward low areas. Ridges may trace the buried crater rim. Changes in brightness may mark variations in composition or roughness. Some features will be geological, others may result from the angle of illumination or the way radar once interacted with the surface. Dragonfly's close images will help resolve those ambiguities. The aircraft will not see a blue pool waiting inside the crater. Any meltwater from the impact has almost certainly frozen long before the mission. The search is for aftermath rather than active liquid on the surface. Yet, frozen ground can preserve a former environment. On Earth, ice traps bubbles of old atmosphere, grains of dust, salts, and traces of biological material. Titan's ice will preserve a different record, shaped by much lower temperatures and different chemistry. Freezing can protect some molecules and damage others. Growing ice crystals push dissolved substances into concentrated pockets. Reactions may continue in thin films of liquid between crystals, even after most water becomes solid. These small environments can last longer than an open pool would suggest. Whether such processes occurred at Selk depends on conditions no model can determine completely. Dragonfly may find clues in the distribution of compounds. A uniform mixture could reflect rapid freezing or later disruption. Concentrated deposits might indicate movement through liquid. Layered material could record separate stages of cooling or sedimentation. The ground will not explain itself directly. Its textures and molecules must be read together. During long periods between flights, Dragonfly can remain on one piece of terrain while Titan moves through day and night. The sun will cross the hazy sky. Temperatures may change only slightly. Winds may shift. The seismometer will listen beneath the aircraft, and the weather instruments will record the atmosphere above it. At a crater site, these background measurements gain additional value. Fractured crust may transmit vibrations differently from compact dune material. Local topography may guide winds. Surface composition may influence how heat moves out of the ground. The crater is not only a destination for sampling, it is a complete environment. Dragonfly's route may conclude near Selk, but the mission's questions continue inward. Beneath the impact-altered crust lies Titan's deeper structure. Far below the surface, water may remain present on a much larger scale, mixed with salts or ammonia, and separated from the atmosphere by many kilometers of ice. The crater cannot provide direct access to that deep interior. Its excavation is far too shallow, but measurements of the crust, seismic activity, and surface composition can contribute to a broader picture of the moon. The water that briefly melted at Selk belongs to the same icy shell that may cover a deep reservoir below. One form of water was temporary and local, the other may be global and enduring. Dragonfly will approach both through indirect evidence. At the crater, chemistry records the local melt. Across the mission, geophysics may reveal how the outer shell moves and responds to Saturn's gravity. Titan holds these scales together. A few molecules inside a drilled grain, a crater tens of miles wide, a crust extending far beneath the surface, an atmosphere surrounding the entire moon. The journey towards Selk moves through each scale without leaving the same landscape. From the air, the crater becomes geography. On the ground, it becomes chemistry. Beneath the landing legs, it becomes a faint vibration traveling through ice. And inside the samples, it may preserve the time when a frozen world briefly held liquid water near its surface. Above every landing site, Titan's atmosphere will remain part of the experiment. It is not only the air that carries Dragonfly between locations, it is the system that produces much of the material the mission has come to study. The atmosphere begins hundreds of kilometers above the surface, where sunlight and charged particles reach gases that have remained around Titan for billions of years. Nitrogen forms the largest share, while methane supplies a smaller but chemically powerful ingredient. Methane does not last forever in the upper atmosphere. Ultraviolet light breaks it apart. Hydrogen can escape into space, while carbon-bearing fragments remain behind and enter new reactions. Without some process restoring methane, its present supply would gradually diminish over geological time. This creates one of Titan's enduring questions. Where does the methane come from? Some may be stored beneath the surface and released through fractures or other geological processes. Some may have emerged from Titan's interior earlier in its history. Reservoirs within the crust could continue feeding the atmosphere in ways that are difficult to observe from orbit. Dragonfly will not drill deeply enough to locate a global source, but it can measure methane near the ground, track changes through Titan's long days, and examine terrain that may contain evidence of past exchange between the interior and atmosphere. The methane already present moves through a climate cycle. Liquid evaporates from lakes, seas, damp ground, and perhaps temporary deposits left after rainfall. Vapor enters the atmosphere. Under suitable conditions, it condenses into clouds and returns to the surface. The cycle resembles Earth's water cycle in outline, though the substances and temperatures are different. On Earth, water moves through oceans, clouds, rivers, snow, soil, and living system. On Titan, methane and ethane occupy many of the visible roles, while water remains frozen into the crust. The comparison is useful because it reveals familiar physics operating with unfamiliar materials. Evaporation still requires energy. Clouds still form when vapor cools and condenses. Rain still follows gravity. Flowing liquid still carves channels, transports sediment, and collects in low terrain. Yet the pace of these events belongs to Titan. The moon receives roughly 1% of the sunlight that reaches Earth. Its atmosphere stores and redistributes part of that energy, while Saturn's long orbit gives Titan seasons lasting more than 7 Earth years each. A cloud system can develop beneath a sky whose seasonal changes unfold across a large part of a human decade. Dragonfly's planned surface mission covers only a portion of that cycle. It will arrive with Titan's climate already moving through a particular seasonal state, shaped by the position of Saturn and the distribution of sunlight between the hemispheres. The mission will observe a limited interval, but within that interval, it may record changes no stationary probe has ever followed. Clouds may appear above the horizon, pressure may rise or fall, near-surface winds may change direction. Methane humidity may vary as the ground warms slightly during daylight and cools again through the long night. These differences may be small from one hour to the next. Over many months, they can reveal how the atmosphere exchanges material with the surface. Titan's lower atmosphere is expected to be relatively calm much of the time. Near the ground, winds may remain light enough for safe flight during planned operations. The dense air still moves, however, and even modest winds can transport heat, vapor, and fine particles. Stronger events may arrive less often. Storms associated with seasonal changes can produce methane rain across broad regions. Cassini observed clouds and temporary darkening on the surface consistent with rainfall. Some storms may send liquids into channels that remain dry for long periods between events. Dragonfly may arrive after such a storm has passed. A darker patch could mark recently wetted ground. A channel floor might preserve deposits carried from higher terrain. Changes in surface reflectivity could fade as methane evaporates or seeps into porous material. The cameras and meteorological sensors can watch these transitions if they occur near the route. A single storm would connect several parts of the mission at once. The atmosphere would supply the methane. Rain would alter the ground. Flowing liquid could move organic grains. Newly exposed or concentrated material might become available to the samplings system. Weather would become chemistry in motion. Even without rainfall, the atmosphere changes how Titan's landscape is preserved. Dense air slows many small objects entering from space. Meteoroids that would strike an airless moon can burn, fragment, or lose energy before reaching the ground. This reduces the number of small craters and contributes to Titan's relatively young-looking surface. Wind and methane rain continue erasing older features. Crater rims soften. Sediment gathers in low places. Channels cut across previous deposits. Dunes migrate around obstacles. Titan is not geologically inactive simply because its surface is cold. Much of its change occurs through atmosphere and weather rather than through the familiar movement of liquid water. Dragonfly will measure the boundary where this atmosphere meets the ground. Near the surface, temperature and wind can vary with terrain. A dune slope warmed by filtered daylight may influence the air differently from an icy plain. A depression may collect colder, denser gas. A ridge can redirect local winds. During flight, the rotorcraft can sample these variations across altitude. It will not climb through Titan's full atmosphere, but even modest changes above the surface can help scientists understand how air moves through the lowest layers. Measurements made at one elevation can be compared with those taken after landing. The aircraft becomes a vertical probe each time it rises. Its motion must also be separated from the environment it is measuring. Rotors create their own wind. Motors and electrical systems produce heat. The body of the vehicle can disturb the air around its sensors. Engineers account for these effects through instrument placement, calibration, and periods of observation when the aircraft is inactive. Some of the best weather measurements may occur while Dragonfly rests through the night. The rotors will not be turning. Heat from the power system will remain controlled within the vehicle. Outside, the atmosphere can pass around the stationary lander, while instruments record slow changes in pressure, temperature, methane abundance, and wind. A long sequence of such measurements may reveal repeating patterns tied to Titan's day. Near sunset, the lower atmosphere may begin to cool. During the night, stable layers can form close to the ground. After sunrise, gradual warming may mix those layers again. The changes will likely be restrained compared with many terrestrial environments, but their structure can still explain how particles and vapor move. Titan's haze affects every day beneath it. The particles scatter visible light, giving the sky its amber color and preventing a clear view of the sun. From the surface, daylight may resemble a heavily overcast afternoon, though the spectrum and brightness would be unlike any weather on Earth. Saturn itself may remain hidden, even though Titan orbits the ringed planet. The thick atmosphere makes the sky opaque at many visible wavelengths. Dragonfly will move across a moon dominated gravitationally by Saturn, while rarely, perhaps never, seeing the planet directly through ordinary cameras. Its presence will still be measurable. Saturn raises tides in Titan's body and atmosphere because Titan follows an elliptical path. The strength and geometry of that pull change during each orbit. The solid crust can flex, and the atmosphere responds to periodic forces. These tides may contribute to winds and may also provide clues about the moon's interior. A body with a deep liquid layer deforms differently from one that is solid throughout. Cassini measurements of Titan's gravity and shape helped support models containing water beneath the crust. Dragonfly's geophysical observations can add local information to that larger picture. Atmospheric tides may appear as small repeating changes in pressure. Detecting them requires long, stable measurements. A single reading means little. Patterns become visible only after many Titan days, when signals can be compared and unrelated weather variations begin to separate from regular cycles. This is one reason duration matters. Dragonfly will not simply visit many places. It will remain long enough for time itself to become part of the instrument. A pressure sensor operating for years can reveal cycles that a brief descent cannot. A camera returning to the same horizon can notice seasonal changes. A weather station carried between sites can distinguish local conditions from patterns shared across the region. The mission's movement adds complexity, but also depth. When wind differs between two sites, the cause may be terrain, elevation, season, or an approaching weather system. Measurements collected along the route allow these possibilities to be tested against one another. Titan's atmosphere also carries information from far beyond the landing zone. Gazes circulate around the moon. Fine haze particles descend from high altitudes. Methane vapor can travel away from its source before forming clouds. A measurement near Selk may contain the influence of northern seas, equatorial weather, and chemistry beginning far above the surface. The local and global systems remain connected. Near Titan's poles, large seas contain methane and ethane in quantities far greater than the liquids expected around Dragonfly's equatorial route. Kraken Mare, the largest known sea, covers an area comparable to one of Earth's inland seas. Other basins, lakes, and channels form a landscape shaped by repeated filling and evaporation. Dragonfly will not fly to these polar regions. The distance is too great, and the mission science is centered on the dunes and Selk crater. Yet the polar liquids still help maintain Titan's climate. They act as reservoirs within a system that transports methane through the atmosphere. Seasonal sunlight shifts the balance between hemispheres. Vapor can move through the air. Clouds form where circulation and temperature permit. Rain may fall far from the seas that supplied some of its methane. The equatorial landscape therefore belongs to a moon-wide cycle. Some channels near the equator may have been carved during rare storms rather than by continuous flow. Their dry appearance between events does not make them inactive features. It means their history is recorded in intervals. A river on Earth may run every day. A channel on Titan may wait years between flows. The landform remembers both conditions. Dragonfly's images can examine channel walls, deposits, and branching patterns. Chemical instruments can test whether low areas contain material transported from elsewhere. Rounded grains or sorted layers may reveal movement by liquid rather than wind. These observations help reconstruct weather the aircraft did not witness. Planetary science often works through such traces. A surface contains the result of events long after the events themselves are gone. The Investigator arrives later and reads what remains. Titan makes that process especially rich because its atmosphere continues to create new material while its weather redistributes older deposits. The sky writes onto the ground. The ground returns methane to the sky. Between them, Dragonfly moves through both parts of the cycle. During each ascent, the rotors and air containing molecules produced across the moon. During each landing, the drills reach material placed by winds, haze, rain, and impacts. The machine never leaves Titan's chemistry, even when it is traveling between experiments. The atmosphere will also determine how Dragonfly communicates. Radio signals sent toward Earth must pass upward through the haze, though the atmosphere is largely transparent at the frequency selected for communication. The more difficult barrier is distance. Titan turns beneath the spacecraft, while Earth and Saturn continue around the Sun. The geometry changes. Communication windows must account for the position of the vehicle, available power, and the orientation of its antenna. Data cannot always be sent immediately. Images and measurements will be stored onboard, compressed, organized, and transmitted during planned sessions. A flight may produce far more information than can cross space at once. The mission team will receive Titan gradually. A selection of engineering data may arrive first, confirming that the aircraft is safe. Scientific measurements follow in carefully managed sequences. High-resolution images can require multiple communication periods. What happened during one Titan morning may take days to reconstruct on Earth. The delay creates a different relationship with exploration. There is no continuous video stream from beneath the haze. There are packets of evidence arriving after the aircraft has already moved through the experience. A horizon appears line by line. A weather record becomes a graph. A chemical spectrum reaches the laboratory. Scientists assemble the event from information carried across more than 1 billion kilometers. While they study one landing site, Dragonfly may already be resting at another. Outside the vehicle, the atmosphere continues its work without waiting for interpretation. Methane molecules rise and fall, haze particles settle, wind presses against dune slopes, clouds may gather beyond the visible horizon. The mission will measure only a fraction of these movements, but that fraction can anchor decades of observations from telescopes, spacecraft, and laboratories. Cassini saw Titan's atmosphere from above. Huygens passed through it once. Dragonfly will live inside it. Across years of flights and long intervals on the ground, the orange air will become more than the curtain that once concealed the surface. It will become a changing landscape of its own, carrying the chemistry of the sky toward every place the rotorcraft lands. By the time Dragonfly reaches the later stages of its route, the mission will have become a record of accumulated comparisons. The first landing site will no longer stand alone. Its dune grains will have been compared with brighter interdune material. Weather measurements will have been repeated beneath different horizons. The aircraft will have crossed terrain shaped by wind, then moved toward ground influenced by impact and water ice. Each flight will carry the earlier sites forward through memory. Inside Dragonfly's computers, images, spectra, pressure records, and seismic traces will be stored as data. On Earth, the same information will be arranged into maps and models. A chemical result from one landing may gain new meaning only after a later sample reveals what was missing before. The mission is built for this kind of delayed understanding. A single measurement can be interesting. A sequence can reveal a process. Suppose the dune fields contain one broad family of organic compounds, while material closer to Selk shows altered ratios among the same molecules. That pattern may indicate heating, exposure to water, or a different history of burial and erosion. Suppose the elemental measurements show increasing water ice as the aircraft approaches impact terrain. The cameras may then identify where darker organic deposits lie against brighter crustal material. The boundary becomes a place to test chemistry directly. Dragonfly can land on one side, sample, recharge, and later cross to the other. No previous mission has been able to make such comparisons across Titan's surface. Cassini observed many regions, but from orbit. Its instruments revealed broad composition, topography, radar texture, and seasonal change. Huygens measured one descent and one landing site. Dragonfly will work at the scale between them. It will see enough terrain to connect separate landscapes, yet remain close enough to examine grains and shallow subsurface material. It can leave one environment and carry the same laboratory into another. This middle scale may become one of the mission's most important achievements. Planetary science often separates global observation from local measurement. Orbiters see whole worlds but miss the smallest details. Landers reveal those details but remain fixed within one limited scene. A flying laboratory joins the two. The route itself becomes an instrument. Distance provides context. Altitude provides shape. Landing provides chemistry. Time provides change. Together, these dimensions allow Titan to be studied as a connected system rather than a collection of isolated features. The system extends far below the aircraft. Titan's frozen surface may cover a deep interior containing liquid water mixed with salts or ammonia. Evidence for this hidden reservoir comes from measurements of gravity, rotation, and tidal deformation gathered during the Cassini mission. The exact structure remains uncertain. Some models place a global ocean beneath a thick outer shell of ice. Others allow for layers of high-pressure ice deeper down, separating liquid from the rocky interior. The thickness and composition of each layer depend on temperature, chemistry, and the moon's long thermal history. Dragonfly cannot reach this ocean. Its drills will enter only the shallow surface. Its flights will remain close to the ground. Yet the geophysical instruments may still detect how the crust responds to forces acting through the entire moon. Saturn continually pulls on Titan, The strength and direction of that pull vary as the Moon moves through its orbit. The outer shell may flex slightly, rising and falling in a cycle too small to see directly but large enough to affect stress within the ice. Cracks may open or shift. Distant impact may send vibrations across the crust. Other movements could originate from processes deeper below. The seismometer will wait for these signals during the long intervals when the aircraft is still. Most of what it records may be local. Wind can press against the vehicle. The ground can settle beneath the landing legs. Thermal changes can produce small mechanical movements within the spacecraft itself. Engineers and scientists must identify these sources before searching for Titan. A vibration produced by the lander has a different pattern from one traveling through the Moon. Repeated events can be compared. Signals arriving from below may show how energy changes as it crosses layers of ice or sediment. Even a small number of natural events could improve models of the crust. The timing and frequency of waves reveal properties of the material they pass through. Dense, solid ice transmits energy differently from fractured deposits. A liquid layer blocks certain seismic waves and alters others. With only one station at a time, interpretation will remain limited. Dragonfly's movement offers a partial answer. A later landing site becomes a new listening point. The aircraft cannot operate as a network in several locations at once, but it can compare the seismic character of different regions over the mission. Dune material may produce one background pattern. Crater terrain may produce another. A fractured impact deposit may transmit vibrations differently from compact ice-rich ground. The mission may begin to describe Titan not only by what lies on the surface, but by how the surface feels from within. That deeper perspective also changes the meaning of Selk crater. The impact that formed it did more than melt local ice. It sent energy into Titan's crust. It excavated material once hidden below and placed it near the surface. It may have opened fractures that later guided heat, gas, or liquid. Some of those fractures could have closed long ago. Others may remain preserved beneath younger deposits. Dragonfly's cameras, chemical instruments, and seismometer approach the same history from different directions. Images reveal structure. Samples reveal alteration. Vibrations reveal the character of the ground beneath them. The mission does not need every measurement to point toward one simple story. Titan may resist simplicity. A chemically unusual sample could have been changed by impact heating, methane weather, radiation, or material delivered by the impactor itself. A bright exposure might be clean water ice, or a mixture covered by a thin layer of organics. Several processes may overlap at the same location. This complexity is not a failure of the experiment. It is the nature of a planetary surface that has been shaped by atmosphere, geology, impacts, and time. The purpose of repeated observations is not to remove all uncertainty. It is to narrow the range of histories capable of producing what Dragonfly finds. Some questions may become clearer, others may widen. The source of atmospheric methane may remain unresolved, but surface measurements could show whether certain terrains release more of it than others. The deep ocean may remain unreachable, but seismic and tidal evidence could refine its depth or the thickness of the ice above it. The chemistry near Selk may not reveal a direct pathway toward life, but it may show how water changes Titan's atmospheric organics. Each result adds a boundary around what is possible. That boundary matters far beyond one moon. Titan is part of a larger family of worlds where chemistry operates under conditions unlike Earth's surface. Icy moons contain hidden oceans. Dwarf planets preserve volatile ices. Comets carry organic molecules from the early solar system. Exoplanets and distant moons may combine atmospheres, liquids, and energy in ways not yet observed. Dragonfly will study one accessible example in detail. Its findings can help scientists recognize which ingredients are common, which environments promote complexity, and which assumptions come only from knowing a single inhabited planet. Earth provides the only confirmed example of life. That fact makes every theory of habitability vulnerable to familiarity. We know that liquid water, carbon chemistry, and sustained energy can support life because they do so here. But we do not yet know how many routes can lead toward biology, or how often promising chemistry reaches a dead end. Titan offers a world rich in organic material, but poor in surface liquid water. It separates ingredients that Earth brings together more easily. Then in places such as impact craters, it allows those ingredients to meet for limited spans of time. This intermittent contact may be scientifically useful, precisely because it is incomplete. A temporary warm environment creates a natural experiment with a beginning and an end. The products can freeze into the surface and remain there, while the larger moon returns to its cold equilibrium. Dragonfly will arrive after the experiment is over. Its role is to examine what remains. There is a patience in that design. The mission does not expect Titan to reveal itself in one dramatic moment. It assumes that meaning will emerge from careful movement, from repeated measurements, and from attention to differences that may at first appear small. A few kilometers can separate two chemical histories. A thin surface layer can conceal older material. A faint seismic signal can change a model of the interior. A molecular pattern can require years of laboratory work before its origin becomes clear. The aircraft thus flights may last less than an hour. The interpretation of each flight may continue for decades. During those brief journeys, Dragonfly will rise into air no human being has breathed and cross ground no previous vehicle has touched. It will see the route from above, choose a safe descent, and settle onto another small part of Titan. Then movement will stop. The rotors will slow. Dust and organic grains disturbed by the landing will fall back through the dense air. The instruments will begin again. On Earth, the mission team will wait for signals already traveling home. Between Titan and the receiving antennas lies an immense distance, crossed only by radio waves and the knowledge encoded within them. A pressure reading arrives, then an image, then a chemical spectrum from a sample gathered days earlier. Piece by piece, the hidden moon becomes less hidden, not because its haze has disappeared, but because one machine has learned to move beneath it. By the final planned flights, Dragonfly may stand far from where it first landed. Behind it will be a path no wheel has marked. The route will exist in scattered landing sites, aerial images, drilled patches, and coordinates stored in mission records. Titan's winds may erase some physical traces, while the scientific record remains. That record will connect sky, surface, and interior. It will show how atmospheric chemistry becomes landscape, how landscape preserves climate, how impacts create temporary water, how frozen ground can retain the products of earlier reactions, and how a world too distant for direct control can still be explored through measured, patient flight. The last destination will not complete Titan. No mission could. The polar seas will remain far away. Much of the crust will remain unmapped at close range. The deep interior will still be known through inference. Countless organic compounds may remain beyond the sensitivity of the instruments, but one region will have been crossed with care. The dunes will have been sampled, the weather will have been watched, the crater terrain will have been approached, and the chemistry beneath the orange sky will have entered human knowledge through a route flown one landing at a time. Long before Dragonfly reaches Titan, its journey will have begun in places filled with ordinary human light, clean rooms, test chambers, workbenches beneath white ceilings. There, the rotorcraft is assembled one system at a time. Panels are fitted around its body. Cables are routed through protected spaces. Instruments are placed where they can survive launch, cruise, descent, cold, and repeated flight. Each part is examined before it becomes unreachable. A fastener tightened on Earth may remain untouched for the rest of the mission. A sensor calibrated in a laboratory may later measure an atmosphere more than 1 billion kilometers away. A rotor tested inside a chamber will eventually push against Titan's dense nitrogen air. The machine carries those rooms with it in another form. Their measurements become limits in its software. Their tests become confidence in its structure. Their careful procedures become the reason it can act alone when Earth is too distant to help in the moment. Dragonfly is scheduled to launch no earlier than July of 2028. Above the rocket, the rotorcraft will be folded inside the protective shape for departure from Earth. It will leave beneath forces far stronger than anything it will encounter while flying over Titan. For several minutes, engines will lift the spacecraft through the atmosphere. Then the planet will fall away. The launch will be brief compared with everything that follows. Dragonfly's interplanetary voyage will continue for about 6 years. It will travel through changing sunlight and deepening cold, following a path shaped by gravity and the motion of worlds. The rotorcraft will remain enclosed, inactive in the way a packed instrument is inactive, while its support systems preserve it for a destination still far ahead. There will be little resemblance to flight during this crossing. The rotors will not turn. The cameras will not watch a landscape pass below. The sampling drills will remain clean. Dragonfly will move because the entire spacecraft is moving, carried through the solar system along a carefully calculated route. From Earth, the mission team will track its position through radio signals. Small corrections will adjust the trajectory. Engineers will monitor power, temperature, and the condition of systems that must remain ready across years of travel. Saturn will grow slowly from a point into a world. Its rings will widen. Titan will emerge as one moon among many, still wrapped in the haze that concealed its surface from early telescopes. Arrival will not begin with orbit. Dragonfly is designed to enter Titan's atmosphere directly. The cruise stage that supported the interplanetary journey will be left behind, and the entry capsule will meet the upper air at high speed. For a time, the spacecraft will depend on a heat shield. The atmosphere that later makes flight easier will first resist the incoming capsule with enormous force. Air compressed ahead of the vehicle will grow hot. The protective shield will carry that heat away while the capsule slows. Then parachutes will open. The descent will pass through layers of haze that earlier missions could study only briefly. Pressure will rise. The air will thicken. Temperatures will approach the deep cold of the surface. Below, the equatorial landscape will remain hidden until the final stages. The protective shell will separate. Dragonfly will be released. Its rotors will begin turning in Titan's air for the first time. That moment will not be commanded from Earth as it happens. By the time any signal describing the release reaches the mission team, the vehicle will already have succeeded or failed. The machine must continue through its own sequence: stabilize, measure altitude, see the ground. Identify hazards, move toward a safe landing region. The first flight will begin before the first landing. Beneath the aircraft, dark dunes and brighter corridors will take shape through the haze. Features mapped by Cassini from far above will appear at close. Range, no longer radar patterns, but slopes, textures, and real terrain. Dragonfly will descend toward one small area within that larger world. Its landing legs will meet the surface. The rotors will slow. For the first time since launch, the vehicle will be still on solid ground. No person will hear the landing directly. There may be vibrations through the frame, the brief movement of disturbed grains, and the changing pitch of rotors as they settle. These events will be translated into engineering data and sent outward as radio to you. The signal will rise through Titan's atmosphere. It will cross the Saturnian system. It will continue through interplanetary space until antennas on Earth receive a faint transmission from beneath the orange sky. Only then will people know that Dragonfly has arrived. The first images may show little at first: a landing leg, a patch of dark material, a low horizon blurred by haze. Yet every visible detail will belong to a place no camera has examined from that position before. The mission will begin carefully. Systems will be checked. Weather will be measured. The landing site will be photographed under natural and controlled illumination. The aircraft will determine how closely Titan's true surface conditions match the models carried from Earth. Later, a drill may touch the ground, a sample may enter the laboratory, a mass spectrum may reveal the first molecular pattern measured by Dragonfly on Titan. Then the long rhythm of the mission will establish itself. Observe, recharge, transmit, plan, fly, land again. There may be setbacks. A destination may prove unsafe. A planned flight may be delayed by weather, power, or the need for further analysis. An instrument may return a result that remains unclear. Titan may offer fewer detectable differences between sites than expected, or more complexity than existing models can explain. Exploration does not require the world to behave conveniently. Dragonfly's purpose is to encounter Titan as it is. The aircraft will carry a plan, but the moon will shape the route. Each successful flight will extend the range of direct experience. The first cautious movements near the landing zone may lead toward longer crossings. Dunes will pass below. Interdune plains will open between them. Selk's impact terrain will draw closer through a sequence of measured steps. The mission is expected to continue for a little more than 3 Earth years after arrival. That span is brief beside Titan's history. Methane has cycled through its atmosphere across ages. Organic particles have fallen through the haze for longer than any human lineage has existed. Impacts have opened the crust. Water has melted and frozen again. Winds have arranged dark grains into ridges stretching beyond the horizon. Dragonfly will enter this long history for only a moment. But a moment can be enough to measure. The rotorcraft may reveal how Titan's organic material changes from one environment to another. It may clarify how dunes are assembled, how methane weather moves across the equator, and whether impact-altered ground preserves chemistry that could not form in colder surroundings. It may hear movement beneath the crust. It may find only faint seismic traces or none that can be clearly interpreted. It may refine ideas about a buried ocean without ever approaching it. Some of its most lasting results may be questions that become more precise. That is often what a distant world gives back. Not a complete answer, but a better boundary between what is known and what remains possible. Years after the final flight, Dragonfly's data will continue to be studied. New laboratory experiments will reproduce compounds detected in its samples. Improved models will revisit its weather records and seismic measurements. Future missions may use its route as the beginning of a larger map. The aircraft itself will remain on Titan. When its power declines and communication ends, it will stand at its final landing site beneath the same dense atmosphere that once carried it from place to place. The rotors will no longer turn. The instruments will become still. Methane weather may pass over the region. Haze particles will settle onto the body. Wind may gather organic grains around the landing legs, gradually joining the machine to the landscape it crossed. Saturn will continue pulling on the moon. The northern seas will continue exchanging methane with the air. The dunes will continue their patient movement across the equator, and far above them, sunlight will keep filtering through the orange atmosphere. Dragonfly will rest where its last flight ended,